Hello everyone, and thank you for joining today's webinar on the design and operational fundamentals of capacitor banks. My name is Ashish Kokne, and I'm Digital Marketing Specialist at Grid Solutions. I'm pleased to welcome you all to our PQP webinars. Let me start with a brief introduction to the webinar platform in front of you, and then hand it off to our featured speaker for today, Dylan Kirkland, Lead Applications Engineer at GE Grid Solutions. If you would like your slides to be bigger, you can expand the slide area or increase it to full screen by clicking on the arrow in the top right corner of the slide area box. If you have any questions during the webcast, just click the Q&A widget at the bottom of your screen. We will answer as many questions as possible after the presentation. If you are having technical issues with the webinar, you can use the Q&A box to ask for help. We recommend logging off your VPN, as well as closing any programs or browser sessions running in the background. Both actions will help your webinar run more smoothly. If the presentation freezes or you lose audio, just refresh your browser, as this will solve the problem in most cases. Everyone will receive a link to the on-demand version of this webinar by email tomorrow. I would now like to turn the presentation over to Dylan. Dylan, the floor is yours.
Thank you, Ash. I appreciate the introduction. So again, my name is Dylan Kirkland. I am the lead application engineer here in Clearwater, Florida for PQP capacitors. So if you guys have requested a quote design or called in for any technical assistance with the fabrication of the capacitor bank or the design aspects, you've probably spoken to me or I've had a direct hand in that design. So what I'd like to do today is we will go through a couple things. So we're going to just start a quick your VAR Compensation Basics, just to go through an overview of that. It's generally something that we probably go through each capacitor bank training, just to have the fundamentals identified. The next part will be the capacitor bank design requirements. So these are going to be everything that I need in order to create a proposal and then create a design for that capacitor bank. After that, we're going to go review the external versus fuseless protection schemes. And then lastly, we'll go through typical maintenance for both externally and fused capacitor banks. So VAR Compensation Basics. So I think we've all seen the beer mug example. So you guys will have to let me know at the end of this how this portrays that same idea with a tube of toothpaste. And the idea is you purchase your tube of toothpaste and you try to use the majority of it, which will be your blue active power. But at the end of it, no matter how hard you try, your KVAR, or the reactive power, is still left over. You still pay for it, but you can't do anything with it. So power factor, it's a measure of how efficiently the current is being converted into useful work output. Okay, the indicator of the effect of the load current on the efficiency of the supply system. Most loads in modern electrical distribution systems are inductive, right? So that's where you have your motors, your transformers, inductive furnaces, air condensing units, which require that magnetic field. So the working power consumes watts and can be read on a watt meter. And that's measured in kW. And that's that kW active power, your blue bar on the right side of the screen. The reactive power, the orange or KVAR, doesn't perform useful work, but circulates between the generator and the load. It places a heavier drain on the power source as well as the power source distribution system. So the reactive power is measured in kV amperes reactive, which is your KVARs. Working power and reactive power together make up the apparent power, and the apparent power is measured in kilovolt amp, or kVA, and that's your apparent power, which is your green bar, which is the total of your toothpaste tube, your kW active power of what you're actually getting, and then your reactive power, which is the unusable. And we'll go further into your power factor, which is your kW divided by kVA, and that would be your ultimate power factor. So the power factor is a measure of efficient output input. So up top you have your active, which is going to be your useful power measured in kW. Going vertically down is your reactive power measured in kVAR. And your apparent power, which is the kVA, and that is the green bar going diagonally down. So that power factor is a measurement of the cosine of theta, of your angle right there, divided by kW versus kVA. So a low power factor means you're not utilizing the power you're paying for, which would be that toothpaste. As kVA decreases as power factor, that increases. So at a 70% power factor, it requires 284 kVA to produce what you're ultimately looking at, active useful power, kW. So your power factor would be measured as 200 divided by 284 kVA equals 70%. So you'd have a 70% power factor. Now, how to improve that power factor? So adding power factor correction capacitors. So we add those capacitors, then we can go from a 70% power factor up to a 95. So you're still getting your 200 kW, but instead of 284 kVA, you're only required 210. And it's that 210 kVA to produce that same 200 kW. And that's where you're going to see your cost savings. So this is going a little more into trying to show an example here of before and after using capacitors. So it's how to calculate the size of a capacitor bank based on target power factor of 95. And theoretically you can go up to 100%, but the maximum benefit is right at 95. So the required apparent power before and after adding a power capacitor bank. So again, you're showing here your 200 kW of that active useful power to turn on a light bulb, to turn a motor, or an inductive furnace, and then 210 kVA, and so you're adding 134 kVAR capacitors. So at that point, at 70% power factor, it takes 35% more current to do the same work. So the name of the game here is adding capacitors to be able to accomplish the same amount of work, and that's what we're ultimately trying to do for a capacitor bank on an electrical system. So, VAR Compensation Basics. So why do we want a good power factor? So the lower total current will translate to a less heat loss in circuit wiring, meaning greater system efficiency. You're reducing your energy costs. You're going to increase the lifetime of components, so those components aren't going to be working as hard as they would without a capacitor bank. You're going to eliminate the penalties from the utility. So utilities will apply penalties for a low power factor. So once you install or implement that capacitor bank, you're going to increase your power factor and you won't have these penalties. And then obviously there's the reduction of your electric bill. We went back to those examples to accomplish 200 kW. And then so this is a table that kind of identifies this. So based off 100% power factor, your real power, your real power at 600, your total power in kVA will be that 600. So if you go down here to a 60% power factor, for that same 600, your total power is going to be 1,000. So here it kind of gives you a good visual example of what you accomplish by increasing that power factor. Okay, so that was the basics of the VAR compensation. And then so what we can do now is we can apply that to our capacitor bank design requirements. So these are going to be the requirements that when you have this identified need for capacitor bank, what you'll come to GE with us, and this will be what I use to design that bank. And so the data needed for designing a capacitor bank. So obviously, on a system, I'm not going to have all these data points, but the more you can provide to me, the better it's going to be, the more accurate we'll get, and just less revisions and going back and forth, ultimately to reduce your lead time to get it shipped out and installed. So what I need to design that capacitor bank is the nominal voltage V and the actual voltage, the line-to-line rated, the needed reactive power, that's going to be in your MVAR, the frequency, whether it's a 50 hertz or a 60 hertz system. Obviously, domestically would be 60. On more international jobs, will be at 50. This is going to be the connection type. So we're going to have either a ungrounded Y, a grounded Y, YY, or a grounded YY. Further along, we'll talk about what we see for most common externally fused capacitor banks, and traditionally, or more commonly, we see an ungrounded Y configuration. And we'll go through the different types and benefits and costs involved with that. Keep going. The insulation level, and this is going to be measured in your kV BIL, whether it's going to be a fused or fuseless, the capacitor size, the accessories, whether we're going to turn it on using a cap switcher or other device, what type of switch that is, CLR, so that's going to be your current limiting reactor on either your inrush or outrush. And then for your protection, we're going to be using a potential transformer, or PT or VT. A CT would be a current transformer, and then some system protections such as arresters. Generally, we put an arrestor on each phase, and then a fourth on your neutral. And then safety equipment like a ground switch, or you can have other things such as ground studs to safely ground the bank before maintenance is performed. So that's the electrical requirements and environmental conditions. So I'll need to know the altitude, and the requirement here is because at higher altitudes, my BIL will decrease due to the thinner air. Ambient air temperatures, so below 40 C, you have that risk of partial discharges, low gradient and element and voltage to be used, and above 45 C, you have a derating of capacitor unit, low gradient, and less current to be used. The capacitor unit internal temperature continuously not more than 65 C, and we have your maximum ambient temperature is 55 C. And so here we get a lot of questions on how do capacitors operate at elevated temperature, and is there a life expectancy decrease due to elevated temperature? And this is something we get asked pretty frequently to a lot of our southeast or southwestern customers, and the answer is capacitors operate in elevated temperatures as expected. There's not really a decrease in life expectancy due to that elevated temperature. The dielectric oil in the capacitor is still viscous. And so where you actually have more difficulty is when you run capacitors in very cold ambient temperatures. And at that point, what happens is your dielectric fluid can kind of start to become less viscous and has trouble with the operation at that point. And then lastly, wind and seismic requirements. Traditionally, GE can provide foundations at 90 miles an hour, but if you're going to include a seismic requirement to that, GE will additionally outsource reactions for that foundation load. A external versus fuseless protection schemes. So this is an example of a externally fused, ungrounded Y capacitor bank. This is traditionally used with our renewables, our solar, our wind customers. So some of the basics about this. It's a commonly used 34.5 kV nominal voltage. It is one substructure. It is about a 10-foot tall substructure. And then everything is mounted on that substructure at 10 feet. So your live parts to ground is going to be 10 feet or greater. The substructure contains your 3 racks. So each rack is a phase. So you'll have your A, B, and C phases, and it is turned on with a cap switcher. Your line connection will come into the cap switcher and feed those 3 phases. It is many capacitor units in parallel within each series. So this example here is one series section. The capacitors, the series wraps around that rack, and so what we have here is looks like there's 6 capacitors on the front-facing side, and you're going to have 6 more, so you'll have a total of 12 capacitors in series. The substructure allows for accessories to be mounted on the same substructure. So what we have here is, you can see we have a ground switch mounted to it. We have a junction box that includes terminals for the PT. We have a PT as the protection, which is going to be monitoring that neutral voltage. And we have 4 arresters, again, 3 arresters for each phase and a 4th arrestor on the neutral. This allows the ultimate footprint to be reduced pretty significantly. So once it's installed out in the yard, the footprint is reduced by not requiring 3 separate substructures. It's about 22 feet tall, 8 feet wide, and 20 feet long. And this dimension is kind of dependent on what that VAR requirement is. As you go greater or smaller, the 20 feet length will either decrease or grow. GE offers a standardized externally fused designs to reduce lead times. So on a standard lead time, and I'm going to share a link later on, which will be a catalog of the externally fused standardized cap banks. That lead time is going to be 16 weeks from placement of order to when that bank will be shipping to your site. And so by utilizing a standard lead time, it allows us for a couple different things. The drawing lead time will be 2 weeks. And if you're to go to a custom capacitor design, that lead time for drawings does increase pretty significantly from 2 weeks to 5 weeks. And then you'll see the ship time goes from 16 weeks to 22. So there's an advantage of utilizing a standard capacitor bank. And so we provide a catalog which will identify MVAR requirements at 34.5 kV, and there's a selection table, and so you can select the MVAR requirements, which will include the cap switcher here, the arresters, ground switch, and a PT. And this is pretty much a standard offering, and we've had pretty good success with this. The other advantage of using a standardized capacitor bank for its externally fused is the capacitors are a standard standard part number. So there's a rolling spare capacitor inventory at the Clearwater factory. So by using this, if there's no spares out on site, in order to get that bank up and energized again, you can place an order with Clearwater, and we can supply those spare units much quicker than a custom unit that will have a much longer lead time. And some systems won't allow for that standardized part, but if it's tolerable, it's definitely recommended. We've had some pretty good success with this. And where custom capacitors are made to order, vary in lead time, there's going to be a minimum number of weeks before that's able to ship. It's a pretty good system. So this is another example of an externally fused bank. But what you see here, though, is going to be, so the first example, go back. The first example is each phase is one parallel, and you had 12 in series. And here you have two series sections, and that's where our elementary diagram is identified here. So here's one series section. The rack is grounded at midpoint. You have your second series section, and each series section is fused. Now, what you see here is your neutrals get tied together, and a PT monitors that for your protection. Over here, we had the line connection come into the arresters, and from each arrestor in series, we came up to each phase. The downside of going to a 2-series capacitor bank here is each rack does need to be insulated, where before each rack was tied in together, now you're adding insulators, which is increasing that cost of your ultimate capacitor bank. So basics here, your line-to-line voltage equals your unit voltage times the square root of 3. So the change voltage, in order to change the voltage to increase the MVAR nominal, so an example here, if we had a 600 kVAR can at 21.6 unit voltage, that will equal your line-to-line rated divided by the square root of 3. The voltage per series section must be 24,940 volts or less. The parallel energy must be 9,300 kVAR per series section per phase. If I go any higher than 9,300 kVAR, then I need to go to more series sections, which is you're going to see a significant increase of insulator cost, of your rack sizes, and your bus connections or pipe. If multiple banks are installed on the same bus, so we'll have customers that will ask for, hey, I have two separate, or 2 or 3 or 4 capacitor banks, but if they're all installed on the same bus and there's no CLRs for inrush or outrush reactors, then they must be included in the parallel energy calculation. enough parallel units are used to limit the overvoltage to 10% of less with one fuse operated. So when we get a request for a quote, we need there's a minimum number of capacitors that I can design in order to provide adequate protection. So if one capacitor externally fused goes, I'm going to alarm off of one, and then if two go, I'm going to trip that breaker. So at minimum, I'm going to need 4 capacitors in series in order to provide adequate protection. So what I'm saying here is fewer units in parallel can be used by rating the bank higher than nominal voltage or using low stress unit that is capable of higher than 10% continuous voltage. Obviously here, you're going to see an increase of cost due to using lower stress units. So if you can factor in or design around the high cost for lower stress units and provide just more capacitors in series, then that avoids that. Okay, 1 series section versus 2 series sections. So the first slide was the 1 series section. So that's commonly a ungrounded Y connection. The racks between phases are intrinsically connected. The potential transformer monitors voltage on your neutral, and this is going to be our lowest cost solution. This is what our standardized externally fused capacitor bank design is. And I generally try to design using this particular method. It's going to be the cheapest for the customer. It's going to be reduce the installation time. And it provides a nice package for a lot of the, again, our renewable customers. Now, when required to go from 1 series section to 2 series section, at that point, the connection type will go to a grounded Y, a GY. The racks are going to be isolated by using insulators between the racks to provide the protection. Instead of a PT, we'll use a current transformer. And that current transformer is going to measure the current traveling on the neutral. So if it sees an increase of current at a certain point, it will trip an alarm. And if 2 capacitors go, depending on your set point, the second point will then trip the breaker and close. And that provides current signal to the control relays. The CT, when sizing the CT or current transformer, it needs to be rated at equal to or greater than 0.2 times the system line-to-line voltage. And again, the higher cost due to the additional insulators. The CT cost is higher than standard PT. So earlier we talked about all the information that I need. So if this part can be left open-ended and I have the chance to design a ungrounded Y versus a grounded Y, I'm going to choose the ungrounded Y just to accomplish a cost reduction. But if it's required, we'll go to the 2 series section here. The simplest method to detect unbalance in single ungrounded Y banks is to measure that bank neutral or zero sequence voltage. The capacitor bank is balanced and the system balance equals 0, the neutral voltage will ideally be 0 as well. And a change in that phase of the bank will result in a change in the neutral or zero sequence voltage, which will then, like I was saying before, it will drive a relay for a alarm or a breaker close. So you can't, it's not just one series section or two series section. You can go upwards of as many as you need to accomplish what the MVAR requirements are and the voltage requirements. So this is an example of an externally fused, a 5 series section, where we're looking at before at 34.5 kV banks. This one was rated at 119 kV, and it was a ungrounded Y. So you can look at your connection diagram here, where you can see each rack. The first rack coming on from your phase has one series section, and that rack is bonded after there. Then you go around to the second rack, and you have 2 series sections, and down to your third, and you have 2 more series sections. You'll also notice you have on a 119 kV system, you have insulators for that required BIL, and a voltage transformer that monitors the neutrals for that unbalance. So one of the common questions that I get is how big can a capacitor bank be? And we talked about that parallel energy calculation. It must be 9,300 kVAR or 24,645 joules per series section per phase or less. The fuses that we use for externally fused are going to be rated for 30 kilojoules or less, and that allows for the cap tolerance, the voltage fluctuations in unwanted harmonics in that system. So these are the calculations for a ungrounded Y bank, a grounded Y bank, a ungrounded Y bank, a ungrounded double Y bank, where we factor in the number of series sections per phase, the number of banks in parallel, and so on the right side I show an example of a nominal 34.5 kV bank. The line-to-line rated is 36.027 with a 28.8 MVAR requirement, and that connection is a ungrounded Y. The capacitor size is a 600 kVAR capacitor. So if I used a 1 series section, that joules calculation, what you see here, I would get 25,459 joules, and that will not be acceptable in the design. It violates that max energy calculation. So where this 1 series section would be the cheapest option for the customer, I required to go to a 2 series section and running through that calculation again. 2 series sections, I get 12,730 joules. And that is sufficient. Okay, how big can a bank be? So enough parallel units are used to limit the overvoltage to 10% or less with 1 fuse operated. Fewer units in parallel can be used by rating the bank higher than the nominal voltage or using less stress units that are capable of that higher than 10% continuous voltage. And here I'm running through the overvoltage calculations for the grounded Y bank, the ungrounded Y bank, and then the ungrounded double Y bank, where the single series section on a grounded Y bank requires a current limiting fuses, since fuses need to break the line voltage to ground. Unless the available fault current is known and less than that fuse tube rating. So on a grounded Y bank at 13 kV if the available fault current is less than 3600 amp, I can use an expulsion fuse. If I can't use an expulsion fuse and you're required to use a current limiting fuse, if it's greater than 3600 amp, then you're going to see an increase in cost on that fuse. All right. This is the protection schemes for an externally fused bank. So if you order the capacitor bank, what GE can provide is that protection scheme. We can provide the trip points and for both the alarm and the relay for the breaker. And this is a screenshot of that protection scheme. So assuming you're using a 130 or 175 dual ratio to 300 PT, your nominal at 34.5, installed VAR at 14. So with one can out, the neutral voltage at rated will be 524 volts. With two cans out, it'll be 1171, and three cans out will be 1991.85 volts. So that dual ratio PT, if we use 524 volts divided by the 175 ratio, that first trip point or alarm will be at 2.99 volts. So that's what's going to drive that first relay for the alarm in the control house. Generally, we set that alarm at 70%, so 2.99 volts times 0.7 for 70%, so your alarm relay will be set at 2.1 alarm. Now, if 2 units go, at that point, you have a pretty significant issue on that capacitor bank, so that will drive to trip a breaker. So we take the two cans out at, we talked about before, was 1171 volt divided by 175 equals 6.69, and I set that trip halfway between my first alarm, which was 2.1 volts, and the 6.69, so I set the second point at 4.84 volts, and at that point the breaker trips, protecting the rest of the capacitor bank. Externally fused. So the fuse link calculation, and this is something that generally GE will provide that calculation. The fuse protection for the capacitor is chosen so the continuous current capability is equal to or greater than 135% of the rated current for grounded Y and 125% for a ungrounded Y. And then this is the minimum fuse link size. Obviously, the smaller fuse link size, the reduced cost. So based on the system requirements, I size it based off of here. And now we can go through some of the typical maintenance involved for these banks. For an externally fused, because you have the fuse tube, the fuse link, and fuse spring, as it says, explains outside of the capacitor, it's a first visual indicator of a potential issue. So from the control house, from a site visit, you can see if that fuse link has is currently present or if it has opened and it is made a disconnect. It minimizes field service to identify the failure and install a replacement. Some of the benefits of the externally fused is it eliminates the need to rewire series connection. So if it is a fuseless capacitor and you have multiple units in series, if one goes, the maintenance team will be required to remove the old and re-terminate the connections there. Also, the externally fused, if the standard unit design is used, a shorter lead time for the replacement caps and spare parts are available, and most commonly available unit sizes are for the externally fused. And so there's really, you see, there's a lot of benefits of ordering a standardized system if you can. Externally fuse some of the accessories we talked about earlier. In order to turn the capacitor bank, open and close it, generally we recommend using a cap switcher, and that cap switcher is sized based on the VAR rating, and really it's the closing resistor size that needs to be sized properly against that VAR rating. The current limiting reactor, and that is typically sized as a function of the voltage. The current rating will be 1.35 times the rated current, and that's to cover the capacitor tolerance, the voltage tolerance, and harmonics on that system. Reactors are used when back-to-back switching is possible. The ground switch, generally we provide a 4-pole ground switch. That fourth pole does protect the and does ground the neutral, but other smaller ground switches that are just going to ground their 3 phases or a 3-pole ground switch are available. The ground switch does include mounting for a Kirk key or similar device, and that is going to be a device that's going to lock out the ground switch and the cap switcher. And this is a safety protocol which requires the capacitor bank to be shut off before the ground switch is operated. Arresters, again, you can have three-phase arresters, one for each phase, or you can have the fourth one on a neutral, and that's sized based on the system MCOV requirements. And when designing for the arrestor, you want the arrestor to be as close to the equipment that you want to protect as possible. So in this example here, we see the arresters are right next to your phase connections and your neutral. That's where it's going to provide the best protection during the event of a lightning strike. Another thing in this example here is you see 2 spare units are mounted on that substructure. This allows for a couple of things. Number one, if the capacitor fails, it's on site already for replacement. Also, during ordering of the capacitor bank, because that does include 2 spare units, the spares are not added to a maintenance budget, separated maintenance budget. It is part of the capacitor bank, and so it's purchased all as one unit. We have a lot of customers that request that. This is the example of the externally fused standardized offering from GE. And so it allows for the quick proposals followed by quick delivery, reduces drawing approval lead time, and this shows the different sizes of bank selections from the smallest 7.2 MVAR 8-unit rack that includes 4 cans parallel, 12 total cans, up to a 28.8 MVAR 16-unit rack. So we talked about externally fused. Now we'll talk about fuseless. Fuseless constructed of elements which are arranged in series and in parallel. provides fail-safe. If dielectric fails in the capacitor, the energy results in a small arc puncturing many layers of film and foil within a single element. The arc then causes the film layer to recede, allowing many layers of foil to touch and weld together, forming an electrically solid joint. This results in the entire series section being shorted. The fuseless allows for higher kVAR units than externally due to fuse limitations. This is an example of a 149 kV, 43 MVAR grounded Y bank at 650 kV BIL, utilizing 600 kVAR units, 6 series sections, and 2 in parallel. This is the elementary diagram of that same fuseless 149 system. Identifies each rack, 2 series sections in each rack. Each rack is then insulated between each other and utilizes a protection scheme using a PT, measures the voltage drop across the low voltage capacitor. That low voltage capacitor is 4 ohm. So we go use V over IR, and that's how that PT does monitor if there's a capacitor that does fail on that phase. Sorry, past one. Fuseless. This is a 138 kV system. Okay, this is a 138 kV system. What we are using here for protection is there is a CT that monitors each string on each phase. So the CT on each string measures the change in current if a failed unit is seen. So advantages here is if there's a failure, the control house knows exactly what string the failure is on, and then the maintenance team can pinpoint it quickly, can make the replacement, and then re-energize. Then the downside is you're using a CT for each string, so it's many CTs equals higher cost, but then you have to evaluate whether that higher initial cost will outweigh the benefits for the quick maintenance time. This is an example of a 69 kV, 47 MVAR fuseless cap bank, 2 series sections, 8 in parallel. The strings are then tied to a neutral, and the CT measures across neutral 1 versus neutral 2. This is going to be a cheaper solution, but again, the maintenance, if one capacitor needs to be swapped out, the maintenance team will then need to go through and identify where that capacitor is. The other issue with this type of protection, if a second unit goes out on the opposite neutral, then that CT will no longer see an imbalance, and it will still show that it is a balanced system. The fuseless, when a short circuit on one unit occurs, an overvoltage results on the unfaulted phases to ensure that the fault is cleared before the second cap failure. And some of the commonly asked questions, and then we will open this up for a Q&A period at the end. So a question I get frequently is a IEEE standard 18. That spec requires discharge resistors to reduce that terminal voltage to 50 volts in 1 minute, or 600 volts for 600 volts, or 5 minutes for greater than 600 volts. Why do I need a ground switch? And so the internal discharge device should not be considered as a substitute for the recommended practice of manually discharging the residual stored charge before working capacitors. It's more than just a redundancy issue. You really do want to have a visual indicator that that cap bank is grounded. The question, why are my 150 kVAR capacitors measuring at 165 kVAR. So per the IEEE allowance, the variance is -0 to +10%. This is due to large variations in capacitor manufacturing. Smaller tolerances would result in higher failed units. Now, the GE manufacturing process, even though the IEEE does allow for that -0 to greater than or 10%, the expected tolerance of a GE capacitor is closer or tighter, and that floats around 3 to 4%, and that is due to a tighter, more refined manufacturing process. What is BIL? The BIL, or the basic impulse level, of my system is a 34.5 kV grounded Y. Why do my insulators need to be 200 kV BIL? And the answer is no. On a grounded Y, as voltage across the stack insulators is 10.5 kV, so 10.5 kV times the square root of 3 equals 18 kV. A 150 kV BIL insulator is rated for 23 kV, so the bank is still rated for 200 kV BIL. Any path between the line and ground is going to be 220. And this example here, the base insulators are only rated for 110, but that is still allowable on a grounded Y system, where every insulator doesn't have to be a true rated at 200 kV BIL. For an ungrounded Y bank, it requires the full line-to-line installation, but that grounded Y requires BIL equal to the last capacitor voltage. And the best way to make that calculation is to determine, is to draw a schematic of the starting arrangement and going through each capacitance. Okay, we'll open it up to a Q&A section. So I will answer these as best I can, and if we run out of time, I can follow up and we can post these answers after the presentation.
Thank you, Dylan. Just a quick reminder that if you'd like to submit a question, please click the Q&A widget at the bottom of your screen. Type your question in the text field and submit. Dylan, I will turn it back over to you to answering the questions. I think we have just over 5 minutes, so you can go ahead.
Hey, Dylan, this is Eduardo. Yep. Can you hear me?
Yep.
Yep, perfect. Good morning. There's several questions already in the Q&A written here, so if you want, we can start from bottom to top. The first one is from a customer in Canada. Why is there a risk of partial discharges at a temperature below -40 C?
That one I might have to review, and I can post that answer. I'll note it, and I'll have to come back to that.
Okay, perfect. The next one is, will the inrush reactors placed used for, in between parentheses, used for a filter-ready option, close parentheses, on line side of the capacitor of each step of the capacitor bank protect the breaker from switching surges?
And the answer is yes. We've used that configuration. It will provide that protection.
Perfect. And the next one is, any ferror-resonance protection scheme for the capacitor banks?
What type of protection?
Ferror-resonance. Ferror-resonance?
Generally, we don't provide that type of protection. using a PT or a CT to measure across that neutral, that type of protection. I'm not super familiar with other methods. Generally, that's what GE will provide, is either a PT or CT option.
Okay. Thank you. The next one is, how do we select whether to use externally fused versus internally fused bank?
So if it's completely open-ended, it's all dependent on cost and the size of that capacitor bank. If it's a smaller bank size, if it's at 34.5, I'll generally choose a externally fused. Going up to higher voltages, you see more cost benefit by using internally fused or fuseless. My design guide tries to give you the cheapest option possible, and then going off of that. So that's generally how I design these.
Okay. And the next one, is there any provision for discharging the capacitor bank via discharge resistor for externally fused capacitor banks?
The answer is yes. So that would be that ground switch solution. We can also add shorting switches to the racks to short out each series section.
Okay. The next one is, what do you see the most Y or delta connected three-phase configuration? I'm not sure why some agencies go with one or the other in terms of application. Can you share some of your experience on this? Thanks.
It depends on, well, the voltage. Generally for lower volt, 34.5 and less, we'll use more commonly a ungrounded Y system. At higher voltages, 49 kV or above, you'll start to see the grounded Y. And that's really, it's dependent on what the system is running at, and I don't know why it switches over after that point.
Okay. The next one is, if any of the fuse blown out, so is main breaker tripped or not, what will be the protection of capacitor bank in case of failure of fuses?
So if like I said, if one fuse goes, generally you want that to be your alarm. It's going to alarm the control house. After two fuses go, that is going to trip the breaker, closing that breaker, removing energy from the capacitor bank. At that point, then you will have to go and identify what the issue was on the system and then replace the fuses.
Okay. The next one is, please share the calculation for fuse rating selection for capacitor banks. I don't know if you have like a table that we can share.
Yep. So after this, I can post that fuse rating calculation and how we rate and size those fuses based on the cap bank requirements.
Thank you. The next one is how to compensate for minus 90 PF.
For the IEEE spec, they are rated for minus 40 plus 40C. We have done applications at negative 90. We can review what the, after this call, we can review what the system requirements are and identify what we can do on that capacitor.
Okay. The The next one is search arrestor voltage level should same lower or higher to the capacitor bank voltage rating?
So generally that arrestor, that MCOV rating, is going to be based on what the system is rated for, not that capacitor bank. So if your system is running at a higher voltage, you want that arrestor to provide protection for the system. So yes, it can be rated higher than what the capacitor bank is. Generally for the 34.5, you'll see a MCOV of around 29 kV.
Okay. Thank you. The next one is, where is the factor of 1.5 in the denominator coming from the fuse sizing?
That's based on the fuse manufacturer. That's where that part of that calculation comes from when identifying what fuse to use.
Okay, thank you. The next one is, in the normal calculation for cap banks, we always try to size for the kVAR needed to improve the power factor. What is the mechanism used to mitigate overvoltage during the light load? Example, when some loads are switched off.
This I'm going to have to review and post that response after.
Okay. The next one is, please share the details for the discharge resistor rating selection for cap banks.
Hey Eduardo, are we out of time right now?
I think we already went 2 minutes over. I know, Ashish, how you want to proceed?
So I think we would have to kind of stop here. So thank you, Dylan and Eduardo, for your time, and thank you everyone for attending. We look forward to seeing you again at our next webinar in this series on fundamentals of air core reactors on May 11th. This concludes today's webinar. Have a wonderful day.
We'll send out the answers later on the pending ones. Thank you.